This lecture is called Electron Gap Calcs, and these are calculations that we do when we're trying to do get a distance factor for electron calculations. So in other words, if we're not treating it, say our normal calculation is 100 SSD and we're going to treat it at an extended distance, maybe 105 or 107, you want to calculate a distance factor for an electron field. That's when we will do a gap calc. Before we talk about electrons, I want to just review really quickly about doing distance factors for photon treatments and where the inverse squared factor comes from. So let's say that we've got a point source of radiation, and radiation is going off in different directions. And we're just going to look at a certain section of the radiation coming from this. And so if we go out, let's say to a certain distance here, we'll call it x, and we look at a little square of that the radiation is going through, and if we follow out in straight lines that square out to say a distance of 2x and compare the amount of radiation at a point here in this first square to the amount of radiation going through a point in the second square, that's going to be our distance factor. Well, the first thing we want to notice is that, let's say this is out at this is a distance x, it doesn't matter what that is, but let's just say that this little square here is 1 meter on a side. Okay, this is 1 meter all the way around. If we go out a distance of 2x, just by, again, these are all straight lines, just by geometry, this side of these squares over here at the distance that's twice as far is going to be 2 meters. So this square will have sides that are twice as big as the sides of this square just by geometry, because this coming in straight lines out from this point, again, it's just similar triangles that if this is 1 meter, this is going to be 2 meters. And we can also say then that this first square here is going to be 1 meter squared, because it's just 1 by 1 meter, and this square over here then is going to be 4 meters squared in area. Okay, it's just 2 times 2 is 4 meters squared. So although the sides of these squares have just doubled because we doubled the distance, the area of the squares has gone up by a factor of 4. In other words, the square of the difference here. So if we look at this back square here and then and divide it up into 4 equal sections, we can see that this area on the area that's on this front square would be the area of one of these little squares of this part here. So we could say that that the same area will be getting 1/4 of the amount of radiation as it was in this first square. In other words, this one has to be now divided up into these 4 sections. And so if we look at just some point in the middle of this square and compare it to a point in this square, we can say that the point back here will be getting 1/4 of the amount of radiation, because that radiation now is divided up into 4 separate squares. And we could do this again if we went out, say, 3 times as far. We had a square that was way out here at if this was a size of 3, this is 3x out here, that this now would be getting, this would have an area of 9 meters squared, and the radiation would be divided up into 9 sections compared to this one here. So anyway, that's what the inverse squared rule means, is that as your distance goes out, the intensity of the radiation goes down by the amount of the square of the distance is proportional. In other words, if you're twice as far, it goes down by a factor of 4. If you're 3 times as far, it goes down by a factor of 9, and so on. And any any thing in between there. We could use that, 1.5 or 2.8, whatever. The radiation is always going down by the square of the relative distances between 2 points from the source. All right, so what does that mean in the clinic? Let's say again, let's say we have a phantom here that we move to 3 different distances from the source here. Okay, so this is the same phantom, we're just moving it away at different distances. Let's say we have a beam that here's our D max for this beam, and let's say we've got a D max of 2 centimeters for this photon. It's a photon beam, and the D max is 2 cm. And let's say that these phantoms are at 100 SSD, 110 SSD, and 120 SSD. And only thing we're going to ask is what is the relative dose at these 3 points, at these 3 distances at Dmax. So that's our question. All right, so let's say this first phantom here, the one at 100 SSD, we set our monitor units. Let's say this is a 10 by 10 field size. We're at 100 SSD Dmax, and we set 100 monitor units. So this and we set our ion chamber there, and we measure that we're giving 100 centigrade to Dmax for this this first field here, for this first phantom. If we move away to 110 SSD, what would we expect to get at Dmax at this point? Well, if we again use inverse squared, the first thing we have to do is figure out what's the relative distances to the source for these 2 points. So the question is, how far away is this point from the source? Now, a lot of people kind of jump the gun, make the mistake to just say, well, that's easy, it's just 100 over 110. That's not exactly right, because it's 100 to the surface, and then we're going to go an extra 2 centimeters down to Dmax. So the real distances here are 102. So it's 100 to the surface plus 2 centimeters. 100 plus Dmax, 102, divided by 110 plus 2, so that's 112. And that's our relative distances, and then we're going to square it. And again, if we just want to think about this for a second, I'm going to say, what dose am I expecting here? I'm expecting it to be less than the dose I get up here. So I want this ratio to be less than 1, which it is. That's how we know we've set up the problem correctly. So let's just see what we'd expect there. We've got 102 divided by 112. We square it, and we get 82.9. So that's what we're expecting to get at that point, would be 82.9 centigrade. And let's say you take you try this out when you commission the machine, and it comes out as pretty close to that. Say it's 83.1. Maybe it's not exact, but it's close enough where we can say that inverse squared seems to work in that case. How about this one over here? Let's say what are we going to expect to measure at 120 SSD? Well, again, if we set up this problem, it's going to be 102 to the first one. 102 is the distance. The distance to this point is 122, 120 SSD plus the Dmax. And if we square that, let's see what we get. 102 divided by 122, and that one comes out as 0.699. So we would expect, if we multiply that by 100, we'd expect to get 69.9. I should say this is I said 80. This is times 100. the front. I'm kind of skipping some math here, but so times 100 of this ratio is how we got this number and that number. So 69.9 is what I'd be expecting here. And let's say I put my ion chamber there and I set it up the same, and I measured, I don't know, let's say it was 70.1 or something. So again, it's close, and we would say yes, inverse squared seems to be working. It's something we can use in our calculations. So we can just use, we don't have to go measure those spots. We can just do inverse squared, and it works for photons. Well, now let's say I did the same thing, but instead of a photon beam, I use an electron beam. And just for convenience sake, I'm going to pick an electron beam that also has a Dmax of 2 centimeters. So I can set up the problem in the same way. In other words, I'm at 100 SSD. We're looking at Dmax, and I set it up so I give 100 centigrade to Dmax here. And I'm going to measure what I get at these points at these different SSDs. And just as a reminder, if we did our inverse squared, if it was a Bayesian inverse squared, we'd expect a dose of about 82.9 centigrade at 110 SSD and a dose of about 69.9 centigrade for 120 SSD. Alright, so let's say I do this. I take a measurement and I take a measurement at 110 at Dmax, and I get something like, let's say, 79.8 centigrade at Dmax here. And then I take a measurement at 120 SSD and I get 65.2 centigrade. So these are quite different than what I'm expecting from inverse squared. So what that tells me is that I cannot use inverse squared simply with the distances, the SSDs. I can't use that for electrons. Why is that? Well, let's switch back to our picture again of these nice straight lines going out here. The reason inverse squared works for photons is because photons travel in nice straight lines, and so if you go out a certain distance from the source, the radiation is spread out nice and evenly, just like you'd expect it to be spread out by geometry. So if we take measurements with our chambers, we get doses that match very closely to what we're expecting just by the geometry, the setup. But why don't we get that with electrons? The reason is that electrons don't travel in nice straight lines like photons do. So let's look at a electron setup. Let's say we've got here's our patient down here, and this thing here is the electron collimator that you put in the head of the machine. This is up actually in the machine. I should probably draw a little more out here, but this is the top of the machine is kind of up like this, and this is this electron cone you put in here. And the way electrons are going to work here is that they come down in kind of a pencil beam, or a kind of a very thin beam coming into this scattering foil, and then they're kind of scattered off of this thing in different just to spread out the beam a bit, and they're traveling and they get sort of collimated or absorbed by this collimators you got hanging down at the patient. So they're moving in a lot of sort of in different directions. They're definitely moving down towards the patient, but they get scattered in the air as well. So even after leaving here, they're coming out relatively straight, but right away they're hitting air molecules and they're spreading out. So that's why first of all, that's why you like to have this collimator as close as you can to the patient. And the electrons are really not coming down in just perfectly straight lines like the photons are. So what happens is that if you move this patient farther away from the electron collimator, the dose will go down because the electrons are spreading out, if you move this farther away, but they're not spreading out in a nice geometrical way from the source, from 100 source to skin distance. If you can't use that as your main distance to figure out how the electrons are going down in intensity. So it's just because of that geometry, the fact that it's not working with electrons, that physicists came up with a factor called the virtual SSD or VSD, the virtual source distance for electrons. Let's go back here. This is how they get the idea of the virtual SSD. So they looked at what they measured. If you say you measured at 110 and 120 and you got these numbers instead of what you're expecting from inverse squared. These are the actual measurements you got. And they said, well, the physicists would say, well, inverse squared isn't working, but if I would pretend that the source of the electrons was not here at 100, but it was in this case, they just do it mathematically and say if I would assume that the SSD was, instead of 100, was, let's say, 82 in this case, and I'm not going to go through the math of how you figure that out, but they just use the measurements they take and say if I would assume an SSD of 82, these would match pretty closely to what I would expect. So let's just try that one. So let's say if I was using an SSD of 82 and with a 2 centimeter Dmax, I would say the inverse squared for going 10 centimeters farther, in this case from 100 to 110, we went 10 centimeters farther, would be like going from 82 to 92 SSD. And if we did our inverse squared, we'd say 84, because that's 82 plus 2 centimeters Dmax, divided by 94 equals that, and we square it, and 79.85. So that worked pretty good. So 79.9, that's 79.8. So yeah, 82 works pretty good for the 110. And let's just try the other one. We have 84 divided by, we're going to go 20 centimeters farther, so that'd be 82 to 102, 2 centimeters Dmax would be 104. Square that and we get 65.2. That's just what we measured. So that looks good. So we'd say, oh, so we can use that if, say, we're going to go to 5 centimeters. We would use what we call the VSD, virtual SSD, of 82 centimeters to figure out the distance factor. And the formula for that is like this. The formula it's called the gap factor, and the formula is just the virtual source distance for that electron cone and that electron energy plus the Dmax is equal to the virtual source distance plus the gap, which is the difference between our case was 100 SSD for our normal treatment down to 110, so the gap was 10 centimeters, the difference between those two, the virtual source distance plus the gap plus Dmax of that beam. So let's say we have a virtual source distance of 82 for this case, and we wanted to know what would be the distance factor if we went from 100 to 105 SSD. So in this case, the gap factor will be our VSD, virtual source distance, which is 82, plus the Dmax, which we said was 2, over the VSD 82 plus the gap, which in this case would be going from 100 to 105, so it's 5 centimeters, plus our Dmax again, 2, and that squared So we got 82 plus 2 would be 84 divided by 82 plus 5 is 89. So 0.891. So since this gap factor is equal to 0.891, if we gave 100 monitor units, we expect the dose at this distance to be 89.1 using the gap factor. Now, if this all seems a little strange to you, it's not you. It is strange because so all you're really doing is saying that inverse squared doesn't work for electrons, but if we take a couple of measurements and make a guess at sort of a virtual SSD, one that's not real, but the electrons are sort of obeying, are coming pretty close, we can use that for getting distance factors for these electron cones. However, I should point out that this is only good for a very short range. In other words, if you went beyond 120, it's probably going to break down. The electrons are going to scatter quite a bit. So you'd really only use it in the range of, say, 100 to 120. You wouldn't use it if you're trying to treat somebody across the room. You shouldn't do that with electrons anyway, but it wouldn't hold up. It only works for a very short range because the electrons are really not falling off according to inverse squared. And so you might ask, well, we basically have output factors here. That's what we measured. If you're measuring these things to get the virtual SSD anyway, why don't you just take a couple more measurements and then have those in the book? You wouldn't have to do this gap calc. But physicists are busy people, and if we're going to say take a measurement at 105 as well and 115, that could take hundreds of seconds, and we're busy people. So we came up with this complicated math way to do it instead of just a simple measurement, and that's so it's really not that it's not that difficult. It just, again, is one of those things that looks difficult. It's just that all you have to do is just whatever the virtual source distance is for that cone and that electron energy, is just pretend that that's what you're setting for your SSD, and then what you use the gap is just what you're really going down. So if you're going 5 centimeters more or 10 centimeters more, just put that in as your gap, and then just otherwise it's just an inverse squared problem, just like you're used to doing with photons. It's just with a different source to SSD, source to surface distance. So that's really all there is to it. And again, it's just a complicated mathematical way to kind of fit the measurements that we get for that cone and that electron energy to something that we can kind of use in a calculation. I will say that I actually don't use gap calcs in the clinic. I'm actually one of those ones that just figures, well, why don't I go and just measure it at some different SSDs, 105 and 115 or whatever I think I'm going to use in the clinic, and I have a book of those as output factors. So in this case, I'd say a distance factor from going from 100 to 110 would just be 0.798. You can do it that way, but again, you're going to be seeing these things on tests for boards and so on, so you'll have to know this gap factor, and some clinics have it set up that way. But remember, it's basically just inverse squared with a different with an imaginary source to surface distance, and it's nothing really to understand physically other than we're just fitting it to a curve by the actual measurements we get in the clinic.